Okay. This previously we were stopped here at parsing, I think. So now we are going to start with the syntax and semantics. In natural language processing, we will use these two words, syntax and semantics, very often. Uh, So syntax is something related to the structure of the sentence. Structure. Film, I think in Arabic it would be something like saha or something like that. I don't know. What is the word for structure in Arabic? Haikal. Okay. Haikal is also, I can understand Haikal also. Uh, anyhow, so syntax is something about sentence structure, huh? When you are doing something to understand the syntax of the structure, that is something you are dealing with the syntax. And similar, oh, yeah, yeah, yeah. You want to move it down. Why? There are lights. No, because we can see probably. Yeah, 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 yeah. So Hmm. I was thinking that maybe I was in a different room with the white blackboard, huh? But this is not that one. So, and then semantics, whenever the word semantics will come, it is always about the meaning of the sentence, meaning of the word, meaning of anything. So, so as far as the definition for these things is concerned, it's easy. Now, moving on to information retrieval. Information retrieval is also a separate course in computer science, but here I think we don't have this course in any program. Either it is CS, either it is IS, either it is what is other one? Software engineering or data science, whatever. This is not available in any curriculum yet. Anyhow, this is important course. So, what is information retrieval? If you want to find, for example, when you are doing some query, and then the system will take your query, it will do something with your query, but leave it at the side at this point. When you will do some query, your system will go into some indexes for finding the relevant documents for that query. And after finding those documents, it will display those documents rank wise. High priority documents first, and then lower priority documents after. This is one example. This is one example that you are doing, you are submitting your query, and then you are getting your response back from the information retrieval system in the form of documents which are relevant to your query, like you are doing on Google search engine, huh? So that search engine is an example of this information retrieval. This retrieval can be in other domain, for example, legal domain. Lawyers, judges, all these people have their system in which they have the legal documents, all legal documents, cases, constitution, other laws, laws of different departments, all laws are there. And then you can build a system over those documents, and then people can do queries that give me the guidance about this case, or give me the guidance about that situation, and then the system will give you those documents which can provide you the guidance about those issues. So so this is how, these are the different examples of information retrieval uh, systems. So now definition is here: finding relevant documents from a large collection in response to a user query. What are the examples? Search engines, digital libraries, books. Library, make it digital, huh? Digital library. Academic search, people are searching articles. Legal documents, retrieval, etc., etc. And then machine translation. I will go to this diagram later on at once. Or you can go it now. Okay. This is the diagram for information retrieval. All the things that we have said, all those things are represented, are depicted here in this picture. So this is a person, he needs some information, and according to his information, he is submitting some query here. So first we are processing that. First the whatever the query is, the system is pre processing your query. So that's why query reformulation. It is called query reformulation, or you can call it query processing. And then after the word, it will come to the real retrieval system that you have designed. And this system is linked with some indexes. And this index, or you can say it has some index, and this index have a corpus. In this corpus, you will have large number of documents available there with index number. Indexing is a technique in information retrieval. You can create index, or you can design indexes of your documents to make your search fast. And there are different indexing algorithms. There are different indexing algorithms in that course of information retrieval, just in the beginning, first 2 3 chapters, through which you can perform this indexing. So here the documents are indexed. This is an index, like you have table of content in your book. The first table of content, this chapter at this page, this topic at this page. This index is like that, huh? so so this system, retrieval system, is connected with this. And when you normally do this query, this retrieval system will retrieve documents from this index according to this query after matching. And there are different matching criterias. Maybe you have already heard cosine similarity or something like that. That is one example, but there are different examples. TF-IDF, term frequency, inverse document frequency. And if you will keep me busy in talking, then the things will come into my mind. Otherwise, it is khali, huh? So, uh, uh, mm, yes. Basically, what is still using what? Sorry again. Basically, as what system? As I don't know. I don't know anything about RAG until I will see its. Uh, I know RAG, but now I cannot say anything wrong. Okay, until I have something in front of me. Your mind is sharp. You can keep your knowledge always in your mind, but my mind is not sharp anymore. I have to see the things first, and then I can say, okay, this is working in that way. This is working in that way. So, so, so now query is there with the retrieval system, and then retrieval system is getting or retrieving documents from by using this indexing technique. And then those documents are coming back here. And finally, this retrieval system is giving you the documents after ranking, high priority first, lower priority after. So ranked, it is giving you the ranked documents. And those documents would be D1, D2, D3, D4. Okay. So this diagram is just giving you an example. That how it will work. Now, machine translation. Its name is easy. You have how we can translate one language text into another language. So if you have some system, that will automatically convert that text into other. This is the model. This picture is just giving you an idea. You cannot understand this picture in deep, but you can have an idea. Here, English sentence is coming. You are converting that English sentence into IDs by using the English dictionary. And then you have English word ID list. Each word will have ID. in the sentence. And then that sentence is going to the transformer neural network, which is coming next in the upcoming slides, and also becoming the base for the large language models. You maybe already have seen this diagram in the course of AI, and maybe in machine learning, maybe in machine learning. If I am giving you a definition of something, deep learning, something like that, then I can come up with this diagram also. But in AI, I am presenting this diagram there for machine translation. So then this is the model, transformer based model. It is converting your English letters into Chinese, and it is giving you Chinese words for that English sentence, and Chinese words in the form of a list, and each word have ID. And then you are using Chinese dictionary back to get words from those IDs, and when you will get your words, then you will have a Chinese sentence as an output. This is a little bit detailed diagram. And here you are giving input, which is English sentence, and then you are generating embeddings for these inputs. Embedding mean embedding vector. Embedding vector is a number. Here, when we are saying IDs, so you are converting the English sentence into IDs. IDs would be numbers, according to the dictionary. According to the dictionary. So input embeddings. So you have some inputs, and then you have ID list, and then after that you are converting into some embedding vector. Vector is again an array of numbers. And then you are adding the positions of the words into this information, which is passed on to this encoder. This is called encoder. And this part is called decoder. This part is called generator. And this is complete transformer model, or you can say deep neural network. Here we have the multi-head attention. Multi-head attention, what is the job of it? The job of this is to calculate the relationship between the different words. And then you are adding and normalizing data, and then after that, these vectors, these embedding vectors, you are passing into feed forward neural network. Again, applying some normalization, and then data is going out. I can discuss it in detail, but when this topic will come at the end, because there is a CLO on large language models, and there is a CLO on machine translation. At that time, we will discuss it with further detail, with some programming stuff also. So, uh, so this is encoder, and the number of encoders can be large. In some models, people are using 5, 12 number of encoders here. And here, the decoders, how the number of decoders, normally it is the same as you have here the number of encoders, but you can increase or decrease also according to your need. But normally they are equal. And if you are using machine translation, then most of the time encoder is compulsion, decoder is compulsion for machine translation only. This was the model first presented for machine translation. This one, this transformer model. Now you have this transformer model you are using for many LLM models. Many LLM models. And most of the time, in different models, you are not using decoder, you are using only encoder. But for machine translation, encoder and decoder is compulsion. And here you have masked multi-head attention. This is a topic. Mask normally means you will hide some information. Huh? It is again the relationship between words, but that information, but this is for the decoder. So here it is English words, here it is Chinese words. This is for the input, this is for the output. Huh? To work this model, if you want that your model, like which is displayed here on this picture, if it will work for this, you need a parallel corpus. A corpus in English with sentences, the same translation of those sentences of English in Chinese here. So you must have a parallel corpus for that. And only then this model will get training over that parallel corpus. And after training, now it would be ready. You can give any English sentence, it will give you the Chinese translation. But first, you need a parallel corpus. Whatever the sentences in English you have here on the left hand side, in one corpus, you will have the same corpus in Chinese for those English sentences. You will translate those English sentences by yourself manually, and then you will keep them there. And it and then you will train that model over those parallel corpus. And here, this is one corpus. You are taking sentences from one corpus, and you are taking sentences from other corpus. So this sentence in English, this sentence in Chinese, going into it, converting it, embedding, adding positions, going into a tension head. This is the same, but it is masked. Okay. Mask is something, used for hiding something. Then after normalization, it is going again to multi-head attention. This encoder is connected to this multi-head attention here, which will again find the relationship between words. It will find contextual things, contextual thing, how the words are dependent on each other. Again, feed forward normalization, and then this ends the decoder. Number of decoder could be any. And then we have a linear. Here you can use uh, soft max or tangent edge or whatever you can use here at the end. And this is what you are modifying your data. Whatever your output that you have here, you are modifying your data, and finally you are getting your data again in numbers. Those numbers would be probabilities. And here you will get some sentence in Chinese that would be most probable translation of your English sentence. Of your English sentence. So this model that you have here, complete model of transformer model, you have here. Now you are using the same model in LLMs, but most of the time you don't have a decoder there in LLMs. But you have this generation. In some models, you have the decoder also. Anyhow, moving next. Here, machine learning, you already know what is the definition. If you have studied the course of machine learning, that is the same thing here. Deep learning, but have a look on it. I will go with some machine learning model. I already told you this. I already informed this thing to you that I will go with such a model that you have not studied in your machine learning course. I will see that which model I will select for this course. And similarly for deep learning, I will select that model. I'm sure that deep learning you have not studied, so I can go with any. So you have studied, yeah. Yeah, some of you maybe have not, but mostly are my old friends. Huh? Okay, so machine learning in NLP. So through machine learning models, we can make our machines able to learn linguistic pattern, because this is a course of NLP. So that's why we are using this word linguistic most of the time. Otherwise, if it would be machine learning, I will use the word data. Okay. Because this is something natural language processing, something about languages, human languages. So that's why we are mostly using this word linguistic patterns, data patterns, you can say. So here, machine learning, through you will have some models in it through which you can make your machines able to learn some linguistic patterns from data instead of relying on manually written rules, which means that you don't have to write if this will happen, then this, if this, if this condition will hold, then this. You don't have to write manual letter. There are machine learning models that can learn the things automatically from your data, even from your raw data, and then predict things accordingly. What are the different models? Naive Bayes. And I have already discussed naive Bayes, I think, in my slides of machine learning. So, logistic regression, very much detailed discussion there in my machine learning slides. Decision trees, yeah, presented somewhere. Sport vector machine, I think I have not done this in my lecture slides there. I think. So, maybe I will go with this one. Random forest, it is there. Definition and some diagrammatical illustration is there. And then deep learning. Deep learning, there is not, so you will see neural network also there in the machine learning, but you will see only the first basic model of neural network here in the machine learning, maybe with one hidden layer. But when you will have deep hidden layers in neural networks, uh, deep hidden layers, you can say more than three, huh? Just an idea, more than three. Up to, you can say, you can make a limit up to three, you can count them in machine learning, but after more than three, because the word deep, hidden layers, when you will have deep hidden layers in a neural network, then that model will lie under the umbrella of deep learning. And deep learning is only about different models of neural networks, different versions of neural networks in which you are using uh, uh, hidden layers. I don't want to say this, but for your understanding, I want to say that when the number of hidden layers would be more than three, and if you have different neural network models, in some model you have different logic, in other model you have different logic, in other model you have different logic, but all models have deep hidden layers, more than three hidden layers, then this is deep learning, huh? And here, but the things that learning type attitude of these models is the same. Machine learning and the deep learning and the NLP learning attitude is same. Learning means getting training. So these models, deep learning models, will again automatically learn complex linguistic patterns or representations by using multi-layer neural network. Multi-layer. Here we have not said hidden layer, but actually we are talking about hidden layers. Input output is one layer, huh, of any program. One program input is one layer, output. We are not talking about this. We are talking about the layers which are in between input and output. So there are different models in it. Recurrent neural network, long short-term LSTM network, gated recurrent GRUs, gated recurrent units, CNNs, and transformers. And I think in machine learning, maybe I have covered this CNN somewhere, which is a model of deep learning. Have you studied machine learning, guys? The students who have studied machine learning, have you studied CNN? Yeah, it is a deep learning model, but when you are ending machine learning, then at the end it will give you a taste for the next course, huh? This is the logic. This is the logic that now you have to take another course, huh? At the end of each course, we will give you some biscuit that will give you the taste for the next course, huh? Anyhow, okay. This is just illustration, pictorial illustration. Okay, it is not something correct view of the things, but it is just giving you idea that how the things are there. So for machine learning pipeline for NLP task, pipeline means what are the number of steps that you have to do if you are going to apply a machine learning model for your NLP task. So first you have a raw text. You will process that text. You will pre-process. You know what is pre-processing steps. You will pre-process that, and you will perform feature engineering also in machine learning. These things are mentioned here. Tokenization, lower casing, we already did that. And then after that, you will convert these, the text, whatever the text that you have, after pre-processing, you will convert them into numbers, into vectors, because model don't understand your text. You have to convert them into vectors. There are models which can understand text, but then that was the history. That history is not existing anymore. Now mostly models are converting your text into numbers, which you are calling vectors. Vector is what? Array of numbers. I don't want to go into the details. Each topic will come and then we will go into it. So here you are converting those text into numeric form by using different uh, uh, approaches. Bag of words is one approach. TF-IDF is another approach. And then when it is vectorized, then you are using your machine learning model. There are different models. We have already given you the names here. Naive Bayes, logistic regression, something like that. You can also see some names here, SVM, naive Bayes. Here your model is getting training over this data because you have divided your data into training and test data. So over training, so your model is getting training over that training data, and then it will have something inside, some numbers, some probability values, somewhere. It will calculate something. That values are basically information. And from those trained values, now you will give them the test data, and from those trained values, it will predict you some other values again. And it will predict you your output, and you can see your output, like for example, if you are doing sentiment analysis about some product, that the comments about the product is positive or negative, so it can answer you like that, positive and negative. If you want to find that the email in your email system, this email is spam or not spam, you can get your answer like that, urgent or normal or whatever. So this is simple example. And similarly, in deep learning, we have only neural network, but neural network with deep layers, with multiple layers, with multiple hidden layers. And these are different models. We already have taken their name. Recurrent neural network, LSTM, GRU, gated recurrent unit, CNN, convolutional and transformer. We will see their details one by one. Now, word embedding. The thing that we were saying previously, that we have to vectorize our text. The word embedding is similar thing. Word embedding means you have to convert your sentence or words in a sentence into the form of embedding vector. You have to convert your words, which you are giving as an input to your model. You have to convert your input into the form of vectors. You can shortly call them vectors, or you can also call them word embedding, or you can also call them embedding vectors. No issue. People are using these different words for the same thing. So, in previous machine learning model here, we converted into ID, and then after that, we are converting it into embeddings. Here you can see input, IDs, and then here input embedding. Now, now, uh, So when you have words, word embedding, vectors, these are normally the terms people are mostly using with some state of the art models. This is an approach which is being used from Glove. Glove is a model, okay? Glove, bird, it was came first in I think 2016, 17, 18. This idea of vectorization, okay? This was the year when I started putting these topics in my classes there in Pakistan. Huh? So this was 2016, 17 or something when this globe and the bird came, and I think in 2018, if I'm not wrong. And still you are using that advanced form of the bird in your LLMs. So anyhow, word embedding. Before that, in information retrieval, you were using TF-IDF and some other things, or you were using your dictionary. That, and if there is a sentence, for example, this is a plane, you will see this. Where in the dictionary this is coming, and in the dictionary, and in your dictionary, the this is coming at position number, at word position number maybe 1001, huh? Now this 1001 is your ID there, huh? Similarly, is where this word is available is, okay, it is available at 2005. This 2005 is now your IDA. In this way, you are making IDs for the words by looking at in the dictionary. But now the next step is convert them into vectors. So now the state of the art, the modern NLP models, or you can say NLP models that we have now, which are good models, you can say not the old ones. They are converting these this list of IDs then into vectors. You can call them dense vector because it is a lengthy, yeah? It is a lengthy array of numbers. And what are the models which are using this idea of word embedding? Word to vec. Word to vec is also a NLP model, uh, which can which during the input phase it is converting your sentences and the words in it into vectors. And then glove, it is also a name of the model, fast text. So these are the first one, eh? And the BERT, okay, S BERT also. So actually these even these two were first, and after that I think this one, and then this one. If we will go with the sequence, this is sequence which is coming into my mind. I can be wrong, but it is coming into my mind. So what is the form of these word embeddings? You can see something like that in this picture. Here, for example, here we have one word and the vector for this is 0.6, 0.6.1. And then there is another word queen and the vector for this, for example, this is not exact example. Just we are saying 0.63, 0.55, 0.9. These vector values normally has some value. And we normally here, for example, x-axis authority. The first value is representing authority. Second value is representing formality. Third value is representing gender. So, and these two values are same, but this last one is different, huh? Which is representing that king and queen also has same status, but their gender is different. This is the meaning of these numbers. This is the meaning of these numbers. So, so the word embeddings that you will have for the words in a sentence, those vectors will have meaning. Okay. Now contextual embedding. Contextual embedding is same. Contextual embedding is same as this one, but contextual embedding has more focus on relationship, on dependency with each other. In a sentence, you can have multiple words in a sentence. How each word is dependent on other. How each word in a sentence has a dependence relation with the other. That relationship will be calculated into the form of probability values. That this word is dependent on that word, for example, 60%. Huh? This word is dependent on that word, maybe 0.2%. Huh? So you will calculate this contextual dependency between the words in a sentence. You will calculate them and then you will represent it into the form of embedding vector. But here we are calling it contextual embedding because focus is more on context relationship. And where we are using it? In transformer models, modern transformer models. Nowadays we are using them. So these transfer models are using these vectors. For example, BERT, and BERT has different versions. RoBERT A, SBERT, GPT, your chat GPT, yeah? What is the benefit of it? Let's have a look. These are the old models, but these are the fathers of these LLMs now you have nowadays, huh? You can say these are the father model of these are the fathering model of these new models that you have now. Difference. What is the difference? Look over here. When there was Glove and Word2Vec and fast text or synth and the things like that, and if you have one word, you know that there can be one word which can have different meaning, huh? You know that, huh? So now when you were using Glove and Word2Vec, now this is one word, and in the corpus, it is giving different meanings in the different positions. But here, this example is giving you the idea that here it will get the same vector for that word, even it is giving you different meanings at different positions in the corpus. But it will get the same vector for the Glove and Word2Vec. Okay. On the other hand, nowadays, when you are using BERT, distal BERT, or LBERT, and we have a ULBERT, huh? Just a minute. We have a ULBERT. Let's see it will come or not. I don't know. I'm just checking. Yeah, it is now coming. Now it is coming, huh? So we have a ULBERT, huh? So for Urdu, maybe I have already spoken to you. Maybe I don't know. So BERT, distal BERT, LBERT. These are some new models. Now, what they are doing in these pictures, so now word is one. This picture or this stats is calculated from the corpus. When this same word is using in some different position and its meaning is different, it is highlighted with green. When it is used, the same word is using within some other sentences with a different meaning, it is highlighted with pink, yellow, blue. So different meanings have different vectors. When the same word is used with different meaning, their vector is different. Here, their vector is same, which means, and here, bird, distal bird, all are doing what? If the same word is used again with different meaning, their vector is different. So what it means? It means how these models are identifying that their meaning is different from context. From context, what is the word behind? What is the word next? From the context, it is highlighting that this here the meaning is different. So now you can say these old models, Glow, Word2Vec, FastX, they cannot distinguish between the different meaning of the same word. They cannot differentiate between the different meaning of the same word. But here, these new models can differentiate like humans. That if, for example, here, this is the example of a bank. The word is bank. Bank can be financial institution, pink color, sloping land, hmm, like on the bank of a river, huh? A bank building, real bank, long ridge, that is same. If with the mountain, arrangement of objects, a flight maneuver. So these are the different meanings and these are the different colors which these models are now showing. But the word is same, bank. And and they have different vectors for that, which means that they are understanding different meanings of the same word, huh? And then showing it graphically. So this is the difference between these new models and the previous earlier model. So these new models are more smarter than the earlier ones. Now, moving next, attention mechanism. We will have the word attention. You have seen in the previous machine translation model, attention, huh? If I will show you. This one, multi-head attention, multi-head attention, multi-head attention. This orange one, huh? So attention, what it will do? Attention mechanism. What this component of the model will do? Or you, because this is a component that now transformer models are using. But what is the abbreviation for this? I think bidirectional encoder decoder representation of transformers, something like that. So BERT is a transformer model. And the models that you have now, GPT, Llama, etc., they are also transformer models. And they have attention mechanism in it. What is this attention? What this mechanism is doing? When I was discussing that, I told you that they will calculate, they will do something, they will find something relationship, they will find some contextual uh, relationship between the words, and then they will, whatever vector you have previously, they will add their own values in that vector. So they will do what? They, in general words, they will identify what are the important words. They will identify what are the important words. This is general understanding. In mathematics, what it means? They will identify those words which will have high probability. Okay. In general, in general meanings, what this attention mechanism will do, they will identify important words. Mathematically, how I can say that? They will identify those words which will have high probability. And transfer model and transformer models, the models that we will have encoder and decoder formation there, they normally call transformer models. So these models process normally words simultaneously at once, in parallel. They don't process words one by one and then second word, then third word in the sentence, and then fourth. No, just in a one go, parallel processing, something like that. They process all words simultaneously at one time using this attention mechanism. You can call it attention, self attention, same thing. And what are the examples for these transformer models? BERT, T5, Llama, GPT that you have nowadays. Now have a look on these diagrams, especially this one, this how the attention mechanism will do the things. This is the pictorial representation of the attention model, what that attention model is doing. The sentence is, I gave her the book she wanted. So for this sentence, the main verb is book. And now, if attention mechanism wants to calculate that how much other words have a relationship with this word book, then how it will calculate? Let's see that. It will calculate the probability. You are saying that for what is the relationship of I with the book? It is displayed it with the gray line, and the probability is 0.05, which means 5%. 5% dependency, 5% influence. And then gave uh, has the uh, relationship with the book. Probability calculated by the attention mechanism is 0.35. And similarly for her, calculated 0.20. And then for the, which is a determiner, it is 0.03, which is 3%. And then she with the book, 0.25. Wanted, 0.15. We are highlighting these probabilities again with the colors here. And then you can identify that this gave and this wanted, and the other word, important words are what? Gave, wanted, and then this 25, she, her, with higher probability. Huh? So from the probability values, from higher to lower, you can identify that these are the important ones. These are the less important ones according to their values. So this context-rich representation of this book, from this book gave. So it means this book is given. This information, this, if you have this vector with these probability values, then we know that this book is given. And given to what? For example, here 35, and then what is next? 25. Book, she. So, and then this information is also there, that book related to or given to she. This information is also there. So these probability values are giving you the meaning in this way. In this way, huh? Because this contextual probabilities are calculated first. Okay, this is just a model for the attention. Okay, this is for, you already know from previous model, input is coming, converting into input embeddings, then we are adding positions into it. Self-attention, what is self-attention? This is a Q key value. You already have heard maybe query, key, and value mechanism in some other subjects. It acts on this basis, and after that it will move on to the feed forward. Then you can calculate. It is mentioned here software, it is wrong here. Okay, software you can calculate, but here after this feed forward neural network. And now large language models, because these are the models which are using these transformer component in it. Transformer is a bigger component than your previous attention component. So large language models are basically transformer models. And the main difference between these transformer models and this LLM is trained on a large corpora, massive corpora. The corpora size is huge, which normally you do not expect in these normal transformer models. And again, the examples are same: GPT, Llama, Gamma, Mistral, etc. So maybe the design is same, but the massive text corpora that you are using for the training of these languages, and the architecture is again displayed here, just giving you an idea. Text is coming, You are first converting text into tokens, which means words. Then you are converting words into IDs and then embeddings. And then it is coming into self attention, then feed forward neural network. This is the same design that you have in the machine translation, huh? This one, this model, attention, feed forward, same. But here the purpose different, there the purpose different. This is transformer model architecture. So this picture is also same, but we are not going into the details of the architecture here, component wise. That previous picture is more detailed. So here if you have transformer layer, which is containing encoders and decoders, and then afterward you will have something as an output into the form of probabilities. And then you can say if the text is doctor reviewed the report, and after this whole process you are getting this generated output, she provided accurate details. This text is generated. You are giving this text, and then the model is generating this text. And normally LLMs are what? They are models that can generate text. Generative AI, huh? You can call them generative AI models. Summary, okay, we have done with the text processing, lexical, what is lexical analysis? We have seen that. And then we have seen the parsing, then we have seen the semantic analysis, we have seen the definition of information retrieval, machine translation, machine learning, deep learning, transformer, LLMs. So now we are a little bit ready to move on to the further concepts one by one in detail. So this is a, if you have your laptops with you, open your laptops, go to the Google Colab and try to type this text and see what will happen. So for example, here for text processing, we are using this library, we are importing it, which is called RE, regular expression, RE. And here text, we are storing this string in this text. And then we are moving text, and the lower function is available. In RE and text.lower, it will convert all the capital letters into lower case. Similarly, remove punctuation. Here we are removing punctuation. And re.sub. And then we have R, and within this, we are saying all words, extract R words as per spaces. And here we have this symbol cap, which means don't do that, which means not operator. Huh? So if so re.sub, and then from here we are saying text. So we are getting whatever we have in the text, we have this thing in lowercase. So we are getting everything from the text. But if that is word or if that is a space, leave it there. And rest of the things, extract it. And throw it. So thee will come, and this is a word. So this symbol is saying don't do anything with it. Huh? Students, don't do anything, don't do anything, don't do anything. So when it will come to this exclamation symbol, huh? It is a word? No. It is a space? No. Not. Then extract it. And it will be extracted and it will be thrown. Thrown out of this text, huh? Thrown out of this text. And whatever the filtered thing, whatever is left from thrown, that is stored here in the text. So all the punctuations will be removed and thrown out, and the remaining will be stored here again in the text. And now we are printing it again, and you are seeing all capital letters. Capital letters are by this one, but this exclamation symbol is thrown by the next statement. So you can open up Google Colab if you want. And I explained you were working, huh? Or means we are making a regular expression now because we were using a library, regular expression. By the way, in NLP, in the first, or you can say second chapter, second chapter is about regular expression, how to write regular expression. I'm not giving anything about, I'm not giving any information about regular expression to you because then there are 4 or 5 different chapters which I skipped. Uh, because I think that you can do the things without them. And if you will, I will give you the information even about the topics to do. Later on in future, you will say, I am not going to use that. So I designed this NLP course uh, in such a way that it will be attractive for you. Okay. This is my approach so that it would be more aligned with your already studied courses, machine learning or something like that, machine learning or deep learning, something like that. So you can check, you can type and check. This is simple one. Okay. I presented here simple codes, short one versions. Next, tokenization. Tokenization, how you can do, how you can split the sentence using into words. So it would be good if you open your laptops and you can try it on Google Colab. You even I can go on with the pie chart here. I have these things already. I have done that already. Okay. This is that code here on one page up to now. Huh? I have already done that. And I was checking something last night here. So, but now I want to make it comment. I was checking other model. What are the models I can have access? For example, I can access Chat GPT, I can access Digital Bert, I can access what are the different models I can access. I was checking this thing. So now here, tokenization. For this, you have to import this NLTK toolkit. We are calling NLTK toolkit. It has many things in it. So we are importing NLTK. And for this, you if you are using PyCharm, then you have to install NLTK by using that command. I always forgot that command. When normally, so what is that? Pip. Yeah. By using pip uh, command, you can use that. From NLTK dot tokenize. So you are importing this, and from this you are using word tokenizer, word tokenize. Again, you are giving some sentence to it. You are using this word. When you are using import, you are importing basically a function from that, huh? Function. And how you normally call a function? Function name and with parenthesis. And here we are calling that function word tokenize with the parenthesis, and we are passing this sentence as an argument to it. So it means that this NL tokenize is something, a library, a class, huh? In which you have many methods there. And from those methods, you are importing again one class from it. And that class has the constructor, the same name. You are calling with the same name, passing this sentence into it. And it will do what? It will split the words of your of your sentence. And then you will have your splitted words in this array, which is containing strings. At zeroth position, it will contain natural 1, 2, 3, 4, 5. It is array. And then we are printing, which it is printing. Words are separated now. Stop word removal. For this, again, NLTK, and there are some corpuses available there. and we are importing stop words from there. There is a corpus of stop words. What is stop word? Frequent words. So it means there is a file there which have words in it, and those words are what? English frequent words, huh? And from an LTK tokenize import, again the same thing. This is the sentence again. And now we are using stop words, this same thing, stop words, and then words, English. We are setting, huh? We are setting English stop words, and all the words are now here. Hmm? English stop words are now, you can say, set. Set is again if a method. We are calling method with this whole thing is becoming argument into it. Take this as an object-oriented programming language, and then you will understand. And then after that, word tokenize, we are passing this sentence into it. It will be converted into words. And now we have a loop. W for W in words. For W in words. So in this word, how many words? 1, 2, 3, 4, 5, whatever the sentence. So for each word, this loop will go on. And then first you are checking if the, and each word will come here in this W, and then you are checking that if this W dot lower, you are converting into lowercase each word. If after converting it, then you are checking not in stop words. In stop words, you have all the stop words. And then you are checking if lower, okay, lower, not in stop words. If it is not available in stop words, what would be the words available in stop words? The, is, am. So then it is checking first the, and then checking not available in stop word. No, it is available. So then it will not work, and then it will fetch next word. It will take next word, and then it is converting next word again into lower. And what is their next word? Students. And then it is checking that students are available in stop words. No, then it will be filtered, and it will go like that. And finally, you are printing filtered, and you are getting these things, which are not stop words. Stemming. Just a minute. Stemming. Stem means something root, huh? It can have a meaning or it cannot have a meaning. So NLTK dot stem, and then import. We are importing Porter Stammer. Porter Stammer is available there, which can do this task for us. So Porter Stammer, this is a function, or you can call it is a constructor. Constructor, when you are using, or if it is a class, when you are using the class name, you are calling the constructor, and an object will be created. But anyhow, this is not my task to give you that understanding. Even programming is not the part of this course NLP, but I will give you these exercises. I will not give you these exercises in the final exam, but I will give you these things, huh? It is not only for you, it is also for me, okay? If I will keep in touch with these things, then these things will be a little bit in my corners of here and there. And if I will not touch them again for a long time, then everything will be washed out. Okay. What is happened? Why the pointer is not working? Yes. So Porter stammer. Object is created, and we have stored the reference here in stammer. And then we have these words playing, played, played. We are initializing an array of strings. And then for word, we are running loop on this. For word in words, it will take one word each time. And that word, we are displaying that word. And then stammer, the same thing. The stammer dot stem. We are saying, so stammer is an object. Stem is a method available in that now. in that class. What class? This class, portal stammer. And then word. And word into it. We are passing this first word into it, and this portal stammer will apply working on it, and it will try to remove this suffix. Huh? And after removing that, it will display something like that. And then it will go for the second word, third, and so on.
Victor,
Hmm.
stammer is playing role lemma here, right?
Porter stammer is providing you stems of the words which you are giving as an input here.
Yeah, it's not like just removing the suffix also. It retrieve the root base of the word, like lemma, lemmatization.
Lemmatization is next.
Oh, because the
Just wait,
the
yeah.
suffix.
Just wait. I was going with the stammer. And by definition, for stemming, we know that it can have a meaning or it cannot. Huh? But lemmatization, something, meaning is compulsory. So now here NLTK dot stem again, and we are importing word net lemmatizer. So now this program is also available there for lemmatization. So we are calling it word net lemmatizer. So this is object creating again like stammer, and here object is created. We have this list, again the same loop, word, and then lemmatizer dot lemmatize. We are calling a function that is available there, passing words according to this loop in it. The first word is going into it, and first word is running. When running is going into it, running is displayed here, and then through this statement, running is displayed. Here it should be run, but word net lemmatizer has not worked here well, huh? So it is giving you the same. Okay, giving us same. That is accuracy, which means his accuracy is not good, huh? But anyhow, for the next, it will take next word children, and it is giving you child here. It is working fine. Hmm? And then for the next word better, it is giving you better because better is not something where you have, yeah, betterment is another word, betterment, huh? But better is something, a root, a lemma. And here, word net lemmatizer will always give you the meaning, huh? And it will try to provide you the root with meaning. But here in this case, running goes to running, it was not working fine, but it's okay. Sometime models can do mistake, and here this is a mistake in word net lemmatizer. But how you can use it, now you can see it here. Part of speech tagging. Telling that which word is noun, which word is adjective, which word is adverb, which word is what. So here again, I am importing NLTK toolkit, and I have this sentence now. Ali bought a new laptop, and then NLTK word tokenize. So in this NLTK, word tokenizer is available. We already used in previous exercise, I think. And we are passing this sentence, and this tokenizer will split the words in this sentence, and all the words will be stored here in this array. We are calling it tokens. What he is doing, huh? Check that. Ah, you are not intelligent man. I was saying to you to secretly check that. Okay. NLTK dot now again using the same NLTK. We are using pose tag, part of speech tag, and we are passing these tokens into it. The array, the separated words. Pose tag is a method available there in NLTK, which can assign the tags to the corpus that we. Now this token is what? It is corpus. Huh? It is like a corpus you are passing. So you are giving corpus which has the separate words in it. Or you can say your sentence is was corpus, which you have separated into tokens after this statement. And now you are giving tokens, words into it. And it will give you tags for those words and which you are printing here. And what will be printed? The word Ali will have NNP. NNP means proper noun. Proper noun. Okay. NN normally means noun. Huh? Here, this is the tagging of Stanford University. Okay. All these things, mostly things which are available in NLTK, is by the students of Stanford University. The modules they built are existing here as an open source. So Ali NLP, which is a what? Proper noun. Bought, it is a verb, but past tense. And past tense verb is displayed according to Stanford part of speech text said it is VBD. Uh, just a minute. We can say, I'll see what, what is the tag for past tense verb in pen tree bank. Look, okay. So pen tree bank, it is also behind this the people of Stanford, and the it is VBD, huh? So now it is confirmed, huh? Where I was. A, the determiner, DT for determiner. New, JJ means adjective, okay? Adjective, huh? And laptop, noun, NN. So these are the part of speech tags. Pentry Bank is, I think it is University of Pennsylvania, I think. Yeah.
University. Semantics. Yeah. University of
Okay. University of Pennsylvania. This was, I think, this was the first tree bank. Maybe some other, but this was the first pioneer tree bank which people used, which give real boost uh, for different NLP tasks, especially related to English language. And that tree bank you can use for extraction of grammar from it, or you can build parser on that tree bank. You can have a part of speech tag set from there also. You can do multiple tasks by using those things. Similarly, okay, I will start from there in the next, or you can do it by yourself. And I will come up with a new CLO, theoretical CLO. Okay, I will go again from here.